All right. Here we go. E equals mc squared. Probably one of the most famous equations in all of science. What I wrote in orange over here is basically a recap of everything we've done so far. A couple of reminders of stuff from 131. So first off, P, what does P represent?
It's been a while for me, so I forgot.
Potential energy.
No, not.
Momentum, yeah.
The P vector, right?
I think
You mean the P vector, right?
Yes, the P vector. And Aaron, say it again.
is momentum.
Yes, it is. And what's the formula for momentum?
Moment. P equal mv
Yep.
mass times velocity.
Thank you, Fulton. All right, Newton's second law. F equals.
Mass times acceleration.
Yes.
That's force.
I was expecting the letters, that's what threw me, when you actually used words. What is acceleration?
The change in velocity over change in time.
Absolutely. Now, I'm going to do the calculus notation of it. It is change in velocity over change in time, but if it's a very small change in time, small change in velocity, we go with dv dt. If it's a larger change in time, then it's delta v over delta t. Velocity?
Position over time.
All right, I'm going to use S for position. Could be S, X, Q, whatever letter you happen to be using. And work.
Is it force times distance?
Close.
That's like the basic one.
Yeah, technically it's force times displacement,
Okay.
officially. So the calculus version of it is force times displacement, but it's integral. But if the force is constant, then we can just get away with force. It's a dot product. If the force is in the direction of displacement, force times displacement. All right. Now a little reminder of doing derivatives. And I know this is not a calculus-based course. All of you have had some calculus, so just sort of a refresher. If P is equal to mv, that's supposed to be an equal sign there. P equals mv, then if I take the derivative of P with respect to z, z can be anything, yes?
Oh, I was about to ask what Z is.
Yeah, z is just some variable. What is the derivative?
I forgot.
All right, let's jump to a simpler one. I was hoping we can jump straight to there. If P is equal to 2 times V, what is dP dV?
1/2.
No P.
Oh,
It would just be 2.
It would just be 2.
oh.
So if I have y is equal to 3x squared dy dx, as you multiply this coefficient times that number right there, and then you subtract 1 from this,
Okay.
or just 6x. Or if y is equal to 5x cubed,
The first derivative would be 15x squared.
yep. Now, that's I have only one variable on the right-hand side. Suppose I have 2 variables. Suppose y is equal to 3x squared we'll just start off this way. So y is equal to 3x squared, then dy dz
6x. So
6x dz.
6x dz.
Close, you got the six x,
Huh.
but then how does x change with z? And so that would be dx dz.
Okay.
So it's known as the chain rule. You first take the derivative of the whole thing right there, so that's six x. And then you narrow it down, so what's the derivative of x with respect to z? And we don't know, so we just leave it like that. Over here, officially, we do the same thing. So we take the derivative of the whole thing, which is six x, and then we take the derivative of x with respect to x. So technically, there's a dx over dx here, but that's just equal to 1, so we generally just ignore it. It's there, but it's 1. But how do you do it when you get two variables here?
We use the chain rule.
Technically the product rule, but
Yep. Products.
what would it be?
Here's the m times the dz plus v times dm on dz.
So you first assume one of them's constant and you do that one, then you assume the other one's constant and you do it that way. That's how you do the derivative if you've got two variables. Now so this is what I have, and if I multiply everything by dz, what do I have? So I multiply this by dz, that by dz, and that by dz.
So all dz cancel out.
Right, and so what I'm left with is dp is equal to mdv plus vdm. Now it's connected to this. I know this is mass times acceleration, and acceleration is this. This was Newton. Newton came up with F is equal to, I'm just gonna drop the vector notation for simplicity, m dv dt. And I'm gonna cut the man some slack here because he invented calculus, as he was doing all this as well. But Newton assumed that the mass would stay constant. You know, he wasn't dealing with rocket problems where it's shooting mass out the back, and he's not dealing with relativistic effects because, well, there's no way for him to possibly know that. If m is indeed constant, I can just take it in and out of that, so this is dmv dt, and so which is dp dt. And so Newton's second law, F equals ma, actually is a specific case for constant mass. And this is the more general case, dp dt. So we'll be using that one again. So force is equal to dp dt. I will put the vector symbols in at this point because when I emphasize direction does matter.
F equals.
And we'll be taking advantage of that. Let's see, the other things that we will need here. Just exploiting this right here. This is, you've got some macroscopic change here, but let's go ahead and assume it's infinitesimally small change, therefore work is going to be infinitesimally small. So I can write that as dw is equal to f ds, and we'll be exploiting that. And let's see what else before we continue. We'll be using that next thing, so let's write that v equals ds dt. V equals mv. dt equals mdv plus vd. Okay. So I think we have all the basics down, plus the stuff that we've done already. And I'm sure all of you are ready for a non-stop thrill ride of math.
Oh boy.
Yes, there we go. That's the enthusiasm I want to see and hear.
You mean the sarcastic enthusiasm?
I'll take it however I'm gonna get it.
Thanks. sounds exhausting, it's just the math part, whew, that's what kills me.
All right, so I've got this mass here. I'm in my Earth frame or your observation frame. You're looking at this mass, and this mass is just moving up in the J direction, in the J hat direction. Fat, dumb, and happy, it's moving at a constant velocity. But then, out of nowhere, a force is applied to it. A force is applied while the thing is between these two regions right here. So what's going to happen when I apply a force in the I hat direction?
It's gonna keep moving in that direction. It's gonna move in its original direction and in the I hat direction.
And in the I hat direction, it's going to get faster and faster. Because a force is being applied to it, therefore it's going to accelerate. And so what this object's going to do is it's going to then, so instead it'll still be moving in the J hat direction, but it'll also start moving in that direction. And at this point I stop applying the force, and so it's now moving that way. Any questions about what this drawing is supposed to represent? All right, so its velocity in this way, it has components. It has an I hat and a J hat component. Let's label them, because life needs labels.
And I assume all this is in a vacuum because no friction.
Right, whatever the force is, we've simplified it down to, it's a thought experiment. I do want to make this use of 0, and that is the initial speed of this thing. So the initial velocity of mass 0 in this reference frame, I guess relative to S is u sub naught j hat, that's just the initial velocity, it's just moving at some value. And u sub naught is approximately equal to 0. It's not 0, it is still moving, but it's just putzing along, and then a mass, this force hits it. So at this point right here, the vertical doesn't change at all, but the horizontal does, and so I'm going to label this as V. So we apply this force to it, and the horizontal part of its velocity is V. Now let's take a look at it from a separate reference frame that's moving along at speed V, the exact same one as that, relative to the S frame. So what is mass 0 going to look like? What is its movement going to look like in this reference frame?
Won't it start off moving diagonally and then accelerate to, or rather, accelerate to a stop and continue moving straight?
Absolutely. So it's going to be moving this way until it reaches when the force is applied. And when that force is applied, it will then move in that direction right there. I believe that's what you were describing with your hand gestures.
Yeah.
And words. So its initial velocity, and let's label those, is traveling to the left at some speed v, and some horizontal component of, let's make sure I do the same labels, u sub 0 prime. And then at this point, it's traveling at some value of u prime. I do need to make one change. At this point, it says u. And the reason why u naught and u are not necessarily the same is that, you get fast enough and suddenly time starts doing funky things. All right. Now let's take care of some of that stuff. F is equal to dp dt. So I have this object traveling in 2 dimensions, so I need to take that into account. So this is going to be ddt of p x I hat plus p y j hat. showing the surprising lack of imagination using x in the I direction and y in j direction. My force is in the I direction, so this is equal to some force in the I hat direction. So from this, well, let's do a quick double check over here. If a I hat plus b j hat is equal to 3 I hat, what are a and b equal?
A 3 and B is 0.
Yeah, similar over here. The I hat parts have to match up, and the j hats have to match up. And so my force, the magnitude of my force has got to be equal to the change in momentum in the x direction with respect to time, and the j hat, the change with respect, the momentum with respect to time is 0. In other words, this is constant. It doesn't change with respect to time. So therefore, my Py initial is going to be equal to my Py final. And this is m sub 0, u sub 0. It's got to be equal to m times u. Because we are working under the assumption that the mass does not stay constant.
I remember you said, mass gets greater with an increase in speed.
Yep, absolutely. Because if it didn't, then a constant force would cause an object to eventually go through the speed of light, which the math says can't happen, so there's got to be an explanation for it. So we have some mass here, because we are sort of working under that assumption that the mass does change. That's got to be the same mass here. And this mass at this point has to be m sub 0. Because how the mass is traveling here and how the mass is traveling here, vertically, basically the same. And the speed of that is pretty much the speed of that. I guess there are some subtle differences there. Let's make sure I have my labels proper. And so vertically over here, so this all comes from that. And so from this one, we have m u naught prime is equal to m naught u prime. So we have these two relationships here, looking at conservation of momentum. And let's do some division. Let's just do some classic stuff. Get away from the world of relativity for a moment, just look at math. I want to get, so I have m u naught prime is equal to m naught u prime, and I'm going to divide the left side by m naught u naught, and the right side by m u. This is legitimate, because the math people say as long as I divide both sides by the same thing, I'm good. So I basically divided the left side here with this, and the right side with that. So looking at this a little bit differently. So I have m over m naught over m. I'm just going to get all the m's on one side and all the u's on the other side. So if I multiply both sides by m over m sub 0, and by u sub naught over u naught prime, what I get is m over m sub 0 squared is equal to u prime over u times u naught over u naught prime. Now recognize that u is traveling perpendicular to the motion. We're dealing with this type of situation right here. The velocity perpendicular to the motion to the movement of the prime frame. I am working with the fact that u naught is really small. And so if u naught is indeed very small, then vy prime in this case, bringing that into it, would be equal to vy divided by gamma. So therefore, m squared over m naught squared equals, let's make sure we get the gammas in the right spot. So when it's traveling perpendicular here and traveling perpendicular there. So we would have u naught prime is equal to u naught over gamma. And in the other situation, we'd have u is equal to u prime over gamma. In other words, u naught prime over u is gamma, and u naught over u naught prime is gamma. So I have m squared is equal to gamma squared times m naught squared, and basically m is equal to gamma. So not relativistic mass, there's the derivation for it. Questions to hear? And that is the biggest step